Before we dive into vector databases, let's start off by comparing them to something we know. First, I created a policy document with pages like this to define rules for a fictional company. Then I created a SQL database, defined a policy table, and inserted one sentence per row into the table's rule column. When I submitted this SQL statement, a full table scan returned one rule. A keyword search ignores context, so it only found the one rule that contains password. Then I created a vector database, defined a policy collection, and added one sentence per item into the documents attribute. When I submitted this prompt, an index search returned 5 rules. A similarity search went beyond keywords and found rules contextually similar to password. Let's further our comparison by looking under the hood. SQL is split into a set of tokens, which are parsed into a tree-like structure that is used to generate a bytecode program. So our relational query works like a typical program. Code written in a high-level language is compiled into low-level instructions. Vector databases work differently. A text prompt is converted into a vector. So our next topic should be vectors. In geometry, a vector can be thought of as a line that has both a length and a direction. If we have another vector, we can compute the cosine of the angle between them and subtract that from 1 to obtain a cosine distance. I'll do the same calculation for another vector, and we have a way to compare them. The smaller the angle, the more similar the vectors. In 2D space, a vector's tip can mark the intersection of two features. Here, the x value indicates 2 legs, and y signifies an average weight of 7 pounds. Let's say this vector represents a chicken. Likewise, 8 legs and 20 pounds can describe a common octopus. So with 2 dimensions, we can loosely describe animals. If we add a third dimension to show that the average lifespan of a chicken is 7 years, and it's 2 years for an octopus, then our description becomes a little more accurate. But the models we use today to turn words into vectors contain many more dimensions than 3. I use Google's embedding model because, as you may know, all of today's leading language models have Google to thank for their technology. For example, when OpenAI published this paper to introduce their first GPT model, the P for pre-trained represents its training methodology, which came from this Google paper, and the T for transformer represents its core architecture, which came from this Google paper. Scrolling through the transformer paper reveals a key innovation. The attention mechanism was a new way to capture language context. Google's embedding model leveraged its LLM's contextual awareness and then fine-tuned it to generate vectors. When I called it to convert these 8 words and then displayed one of the vectors with Python, it had to print an ellipsis because each vector contains 3,072 dimensions. Unlike my example, where we know the 3 dimensions represent legs, pounds, and years, we don't know what any of these dimensions represent. Each one describes an abstract feature the model found useful for identifying differences. I want to show how accurately the model encodes these words, but I can't draw points with over 3,000 dimensions. So I used a reduction technique to display them on a 2D plot. Similar vectors are revealed in clusters, illustrating the efficacy of the embedding model. While the model generates a vector for each of the 7 words in this sentence, it distills the meaning of the entire sentence into a single vector by computing an average for each of the dimensions. I used dimensionality reduction on the vectors for 4 sentences so I could plot them. 2 of the sentences contain the word table, and 2 contain the word shelve. Because table and shelve are encoded based on context from neighboring words, the judge decided to table the motion was given a vector similar to the counsel chose to shelve the law. However, he ordered a new coffee table online, got a very different vector than she had to shelve the returned library books. I'm going to finish summarizing vector databases by using LangChain, which is an open source app building framework used to leverage a language model by chaining it together with other components, like an embedding model and a vector database. After a language model is trained using text from publicly available documents, it can be fine-tuned with text from our company's private documents. The problem with this approach is that anyone who queries the model will have access to our private data. Here's another approach. An internal app can augment each prompt with text it retrieves from our private documents. I'll use this technique to describe vector database operations. Text from our policy PDF is copied into a Python document object. Each policy rule is copied into its own document. Google's embedding model converts each into a vector. A graph-based index is built where nodes represent vectors and edges represent cosine distance. The text of each policy rule is copied into a relational table, and the index is copied into a binary file. When a user enters a prompt, the same embedding model converts it into a vector. A search algorithm traverses the graph to find the most similar vectors and returns their IDs, which are used to fetch the corresponding policy rules that are sent as context for the user's prompt, and a context-based response is returned to the user. LangChain's chat prompt template was used to send all the required data to our chatbot. I predefined a system prompt to instruct the LLM to act like a friendly HR rep and to only provide answers retrieved from our vector database. There's a spot for the prompt a user will enter and a place for documents that will be fetched from our vector database. In conclusion, I'll show how our app responds to this prompt. The chatbot generates this text. The parts in yellow came from the LLM, a friendly introduction at the top and a friendly conclusion at the bottom. The body of the response came directly from our vector database. I hope you can see now why vector databases have become so popular.